Usually, diagnostics are about looking at what's already there. Like taking an x-ray of a broken bone, right? You see the jagged line and, well, the problem is identified.
Right, it's a known physical reality.
Exactly. But in climate machine learning, we're trying to use that same x-ray machine to take a picture of a bone that hasn't even grown yet. And for you listening, whether you spend your days, deep in Earth system modeling or maybe building machine learning weather emulators, you know exactly what the holy grail is right now.
Oh, absolutely. It's the ultimate extrapolation problem.
Yeah. We want to know if an ML model trained purely on the climate of the past can accurately predict a future it has literally never seen.
Which is incredibly difficult. I mean, can a historically trained neural network simulate a world with, say, 4 times the carbon dioxide?
Yeah.
Or are we just building these sophisticated curve fitters that will just completely hallucinate the moment we push them out of their training distribution?
And that is exactly the core question of our source material today. We're looking at a 2026 paper by Mahesh et al. It's titled Examining Fast Radiative Feedbacks Using Machine Learning Weather Emulators.
It's a fascinating piece of work.
It really is. Our mission for this deep dive is to explore how a uniquely modified ML architecture can actually emulate fast radiative convective adjustments without ever being retrained on prospective Earth system conditions.
Right, and what that actually means for the future of climate projection workflows, especially as we, look toward CMIP7.
Okay, let's unpack this. Because to understand how they pulled this off, we first have to talk about why we would ever expect this to work in the first place. I mean, why should an ML emulator trained on ERA5 or EAMV2 data from the 2010s have any clue what a 4 by CO2 atmosphere looks like?
Well, that brings us to the fundamental physical distinction that this entire paper really hinges on. It's the difference between fast and slow climate feedbacks.
Right, because we usually just think of the slow ones.
Exactly. When we think about the Earth's response to greenhouse gases, we tend to focus on those slow feedbacks. We're talking about the decadal changes, deep ocean warming, or ice sheet melting.
The really massive, sluggish, systemic shifts.
Yeah, and those slow feedbacks create climatic boundary conditions that have absolutely no recent historical analog. So if an ML model is trained on just the last 40 years of data, the physics of those completely novel ocean states simply aren't in the training set.
The model hasn't seen the ice caps melt, so it just doesn't know how the atmosphere behaves when they are gone.
Which is an undeniable limitation. But fast feedbacks are a completely different story. Fast feedbacks are driven by atmospheric radiative and convective processes, specifically radiative convective equilibrium, or RCE.
Okay, so RCE is basically what brings the troposphere into thermal equilibrium, right? It balances the radiative cooling with the latent heat released when water vapor condenses into clouds.
You've got it. And based on the global atmospheric water content and the global mean rainfall rate, RCE adjusts on a characteristic timescale of roughly 1 week.
It's just 1 week?
Yeah, 1 week.
That's just the natural turnover time of water vapor in the atmosphere.
Exactly. It is orders of magnitude faster than the thermal response of the upper ocean. So this means that during the first month after a sudden, massive spike in CO2, the global mean sea surface temperatures barely change, maybe by like 0.1 degrees Celsius.
Wow, so almost nothing.
Right. The solar insolation and the sea surface temperatures remain essentially identical to present-day boundary conditions.
So the physics governing these fast radiative convective adjustments are already fully operative today. They're buried inside the historical training data.
Precisely.
It's kind of like the difference between testing a runner's immediate reflex versus their long-term endurance. The ML model has already seen millions of reflexes in the historical weather data.
That's a great way to put it.
It already knows how the atmosphere flinches when it gets poked, because it's learned the fundamental relationship between temperature, moisture, and precipitation under fixed boundary conditions.
And what's fascinating here is how the authors actually isolate that reflex.
Mm-hmm.
They run 96-member ensembles of 1-month rollouts.
Oh, so they keep them super short.
Very short, just 30 days.
Yeah.
And by using that massive ensemble, they can completely filter out the chaotic weather noise that normally dominates after a couple of weeks, due to the natural limit to predictability.
Or the butterfly effect stuff.
Exactly. So if the ML emulator has truly learned the underlying physics of RCE from the historical data, it should theoretically be able to reproduce the exact hydrological response seen in full physics-based Earth system models, like the abrupt 4x CO2 CMIP6 experiments.
But I'm actually really curious about how they physically poke the model.
Mhm.
Because if you take the standard AI2 climate emulator ACE, it's auto-regressively predicting the atmospheric state.
Yeah.
And as far as I know, the version of AC they're using doesn't even have an input variable for CO2 concentrations. There's literally no dial to turn up the greenhouse gases.
No, there isn't.
So how do you simulate a 4 by CO2 world in a model that doesn't even know what CO2 is?
That requires a highly creative methodological workaround. They built a hybrid design coupling ACE with RRTMG.
Okay, RRTMG, that's the rapid radiative transfer model for GCMs, right?
Right. It's a trusted, purely physics-based radiation code used in flagship models like E3SM. So here's what they do. At every single 6-hour inference time step, ACE predicts the global atmospheric state.
Okay.
Then they pause the ML, take that state, and feed it directly into RTMG. RTMG calculates the clear sky radiative heating rate for that exact atmospheric profile, assuming a 1x CO2 world, and then calculates it again, assuming a 4 on CO2 world.
Oh, I see. So they just find the delta between the two.
Exactly. They subtract the 1x CO2 heating rate and add the 4 on CO2 heating rate. In the troposphere, this translates to a heating perturbation of roughly 0.1 Kelvin per day.
That's tiny.
It is, but it's consistent. They add that tiny physical tweak directly to ACE's temperature field at each pressure level, and then they let ACE predict the next time step.
Okay, I have to push back on this a little bit, though. If we are bolting a traditional physics engine onto an ML model to handle the forcing, isn't that cheating?
How do you mean?
Well, are we really proving that ML can handle climate change, or are we just using a physics model to hold its hand? Like, is this just the neural GCM approach in reverse?
That is a really valid question, but distinguishing this from neural GCM is actually critical for understanding the architecture here. Neural GCM is a hybrid model, but its setup is the exact inverse of this.
Right, because neural GCM uses a traditional physics-based dynamical core to solve the fluid equations on a spatial grid.
Yes. And it uses ML specifically to parameterize the subgrid processes, the messy, hard-to-resolve physics like convection and clouds.
So in that case, the ML acts as a very smart, very fast parameterization subroutine inside a physics loop.
Exactly. But the ACER-RTMG framework flips that entirely. Here, the ML emulator is the core. ACE is entirely responsible for the global atmospheric state evolution, the dynamics, the advection, the moisture transport, all of it.
Oh, okay, so the physics-based radiation scheme is only used to control the external forcing.
Right. ACE itself never actually knows that CO2 has changed. It just suddenly feels this consistent 0.1 Kelvin per day anomalous heating from the radiation code.
I see. So the heavy lifting of figuring out how the hydrological cycle should respond to that heating light, like how precipitation and latent heat flux should shift to maintain equilibrium, that's entirely up to the ML.
Exactly. Isolating the forcing from the response allows us to rigorously test the ML's learned in physics.
So we're trusting the physics to apply the heat, but testing the ML to see if it sweats correctly.
That's a perfect analogy.
No.
And initially, well, it didn't sweat correctly.
No.
No. When they first ran this hybrid model using the default ACE architecture, it completely failed to match the physics benchmark. The physics-based EAM-V2 model shows global mean precipitation decreasing in the first month to maintain RCE. But the default ACE model predicted precipitation would just keep increasing.
Wait, really? What exactly is the default architecture learning that throws it off so badly?
It all comes down to the model's spatial inductive biases. The default version of ACE is built on a spherical Fourier neural operator, or SFNO.
Right, SFNO, which is incredibly powerful for weather forecasting because it has this massive global receptive field.
Exactly. It uses spherical harmonic transforms, meaning it mixes all global information together to predict diagnostic outputs at any single point.
So it can look at a storm system in the Pacific and use that context to adjust its prediction for rain in the Atlantic.
Which is great for weather. But that global vision becomes a fatal flaw when you apply a global uniform forcing. Think about the historical training data. In the real world, the tropics are naturally the warmest part of the globe, right?
Yeah, and they're also the rainiest.
Right, because SFNO sees the whole globe at once. It learns a spurious spatial correlation from that historical data. It learns the heuristic that a globally warmer atmosphere is just correlated with more rain everywhere.
Oh, wow. So when RTMG applies that uniform 0.1 Kelvin per day heating across the entire troposphere to simulate elevated CO2, SFNO looks at this globally warmer state, applies its historical spatial correlation and completely misses the local thermodynamics.
It completely misses it. It incorrectly diagnoses a massive global increase in precipitation.
Here's where it gets really interesting, because we so often assume in the AI world that giving a model a global view makes it smarter. Like more context is always better, right?
It's a standard assumption, yeah.
But here, that massive receptive field is exactly what causes the model to hallucinate a physically impossible climate response. So how do they fix it?
They fix it by restricting the receptive field. They basically reintroduced a concept that physics-based GCMs have used for decades, the column local abstraction.
Oh, okay. Because in a traditional DCM, precipitation is calculated using only the state variables of a single vertical atmospheric column.
Exactly. The code doesn't care what's happening halfway across the world. It relies purely on the thermodynamics right there in that specific grid cell.
Tunnel vision.
Tunnel vision. The authors modified the ACE architecture so that the diagnostic variables, specifically precipitation and latent heat flux, are no longer predicted by the global SFNO. Instead, they built a separate, nearly column local neural network.
You say nearly column local. What does that mean?
Well, they use a 3x3 grid cell patch. Given their roughly 100-kilometer horizontal resolution and their 6-hour time step, a 3x3 patch allows the network to account for weather phenomena propagating at speeds up to 83 meters per second.
Okay, which is fast enough to capture local convective organization, but strict enough to prevent the network from memorizing those spurious global temperature correlations.
Exactly, and the results are striking. By forcing the network to diagnose precipitation using only that local 3x3 patch, the modified ACE perfectly matched the physics-based ESM.
Wow.
Yeah, global mean precipitation dropped, latent heat flux dropped, and the spatial patterns of the hydrological response aligned beautifully with the benchmark. The tunnel vision literally saved it.
That is a massive lesson in network design. But it makes me wonder about the engineering burden here. If I'm listening to this and I already have a massive pre-trained SFNO model that I've spent thousands of GPU hours spinning up, can I just staple this 3x3 diagnostic patch onto my frozen backbone, just retrain the diagnostic head and call it a day?
It's a very tempting shortcut, but the supplementary results in the paper show that it absolutely does not work.
No, it doesn't.
Not at all. If you freeze the pre-trained SFNO backbone, which handles the prognostic state evolution, and only train the column local network to diagnose the precipitation, you get a severely muted response to the CO2 forcing. It fails to capture the true magnitude of the fast feedback.
But why? Why does freezing the prognostic backbone break moisture conservation mathematically? I mean, if the backbone already knows how to advect moisture and predict the weather perfectly well, why does freezing it ruin the climate response?
Because maintaining radiative convective equilibrium isn't just about predicting rain at the end of the pipeline. It requires deep interactive coupling between the prognostic state and the diagnostic fluxes.
So they have to talk to each other.
Constantly. Precipitation, evaporation, moisture advection, and the specific humidity at every vertical level, they all have to be tightly constrained together to conserve mass and energy. If the backbone is frozen, it doesn't know it needs to adjust its internal representations of moisture transport to satisfy the new constraints imposed by the local diagnostic patch.
That makes total sense.
So the authors found that for these ML components to couple effectively, the SFNO prognostic network and the column local diagnostic network must be co-optimized. They have to be trained jointly, end-to-end, from scratch.
It's a great reminder that piecemeal ML components often fail when dealing with complex emergent properties like moisture conservation. You can't just slap a new steering wheel on a car without physically connecting it to the axle and expect the transmission to know what to do.
It's exactly. Which brings up a massive engineering hurdle. Computational optimization. Coupling a full radiation code like RRTMG is really heavy. At each time step, the ACE prediction on an NVIDIA A100 GPU takes about 0.35 seconds. But the call to RRTMG on a CPU takes 8 seconds.
Ouch. So the physics engine is bottlenecking the incredibly fast ML emulator by a factor of over 20.
Yes. It's a huge slowdown.
If I'm leading an ML climate group at another lab, I might not want to spend the engineering time to couple RRTMG just to see if my model hallucinates its fast feedbacks. How can the rest of the community test their models for physical fidelity without this huge computational heavy lift?
The authors actually anticipated this, and section 4.5 of the paper is just a gift to the entire ML climate community. They developed an idealized perturbation benchmark that requires zero external physics code.
Zero.
Zero. It is a brilliant first principles derivation. Instead of calculating exact CO2 forcing with a radiation code, you just apply a simple stylized dipole heating profile directly to the model.
Here, what does that look like?
You basically impose a slight cooling in the stratosphere and a uniform heating in the troposphere.
So you're just manually injecting a set amount of heat, say 1 Kelvin per day, into the temperature field.
Exactly. And because it's fixed energy injection, you can use fundamental thermodynamics to calculate exactly how the model's precipitation must respond to maintain equilibrium.
Oh, this comes down to the Bowen ratio, right? Which is the ratio of sensible heat to latent heat.
Spot on.
Wait, walk me through that math, though. I know the Bowen ratio is sensible over latent heat, but how does injecting 1 Kelvin of heat give us a hard physical millimeter per day limit on rain? I'm sort of missing the bridge there.
Let's break down the thermodynamics. In the EAM-V2 training data, the Bowen ratio is 0.23.
Okay.
That means 81% of any energy imbalance at the surface is balanced by latent heating, and the remaining 19% is balanced by sensible heating. Now, latent heating is literally the energy released when water condenses to form rain.
Right, the phase change.
So if you inject exactly 1 Kelvin per day of heating into the atmospheric column, 81% of that energy must manifest as a change in latent heat flux to maintain RCE. You can mathematically convert that required energy shift into the sheer mass of water needed to produce it.
Oh, so directly translate.
Yes. When you do that conversion, it dictates that the precipitation must drop by an amount between 2.27 and 2.60 millimeters per day.
That is incredibly elegant. You don't need a supercomputer or a complex physics loop to run that benchmark. You just apply the dipole heat, run the model, and if the global precipitation doesn't drop by exactly 2.27 to 2.60 millimeters per day, your model is violating the fundamental conservation of energy or water or both.
Exactly. If we connect this to the bigger picture, it really changes the validation game. The default ACE, with its global spherical harmonics, failed this math test completely. It fell wildly outside that acceptable thermodynamic range, but the column local ACE passed it perfectly.
It gives any developer building an ML parameterization or a full emulator an immediate, cheap sanity check to ensure their architecture respects spatial physical constraints.
It does. It's a beautifully rigorous test.
But, as with all bleeding-edge research, we do need to examine the blind spots. This is a massive leap forward for the viability of using ML and CMIP workflows. But what are the caveats here? Where does this methodology still fall short?
The authors are actually very transparent about the limitations, highlighting 4 main areas. First, this is a clear sky-only perturbation. ACE doesn't explicitly emulate cloud condensate as a separate prognostic variable, so this entire experiment ignores cloud feedbacks.
Oh, wow. Okay, what else?
Second, this is an atmosphere-only setup with fixed sea surface temperatures, so there is no slow ocean coupling yet. Third, there are noticeable discrepancies in the land-sea contrast. And finally, there's the issue of deterministic blurring caused by their loss function.
Let's dig into that first one. How does ignoring cloud condensate mask secondary thermodynamic adjustments?
Well, clouds actively reflect shortwave radiation and trap longwave radiation. By running a clear sky-only simulation, we miss the feedback loop, where changing cloud cover would alter localized heating rates.
Yeah.
And those altered heating rates would then feed back into the atmospheric circulation and precipitation patterns.
So it simplifies the problem but removes a highly sensitive climate variable.
Precisely.
And I guess we are only seeing half the climate picture with the atmosphere-only setup. We're tracking the fast half, but completely ignoring how the deep ocean will eventually react.
Right. Furthermore, the land-sea contrast discrepancies show that we haven't perfected the surface interactions either. The benchmark physics model, EAM-V2, shows much higher terrestrial precipitation increases over places like South America and Africa in response to CO2. But the ACE model mutes that oceanic versus terrestrial precipitation difference.
Is that because the ML is smoothing out the sharp gradients in surface roughness or heat capacity between land and water?
That's the most likely explanation, yes.
Which naturally brings us to the deterministic blurring. They used a mean squared error, or MSE, loss function. Why does optimizing for MSE structurally guarantee that we watch out the extremes in high variance systems like heavy rainfall?
Because MSE heavily penalizes large numerical errors. When a model faces multiple possible chaotic weather outcomes at a 6-hour lead time, the safest way to minimize a mean squared error penalty is to predict the statistical average of all possible futures.
So it literally blurs the precipitation field.
Exactly. To capture the tails of the distribution, the severe droughts or flash floods, The field is aggressively moving toward generative approaches and probabilistic loss functions, like diffusion models.
That makes sense.
MSE is a stable starting point for predicting the mean state to extract the RCE response, but it structurally limits our ability to predict extremes.
So what does this all mean for you listening? Whether you are building ML parameterizations for the next generation of ESMs or preparing to run massive ensembles for climate projections, the key takeaway is that architectural inductive biases matter immensely.
They really do.
You cannot just throw 40 years of historical reanalysis data at a transformer or a spherical Fourier neural operator and expect it to magically learn the laws of thermodynamics. Giving an ML model the right data isn't enough. You have to enforce the right spatial abstractions.
Right. Forcing the network to act like a physical column of air, using that 3x3 patch, and coupling it with hybrid physics is what allows us to safely push these historically trained models into unseen boundary conditions. It proves that ML can handle out-of-distribution climate forcing, provided we constrain its hypothesis space correctly.
It's a huge step toward trusting AI with the future of our planet's climate, but it does leave us with one final, very large question.
Yeah. We've proven today that historical ML models can capture fast feedbacks because the physics of water vapor turnover and RCE operate on weekly timescales. Those physics are happening today. But what happens when climate change pushes the Earth past a tipping point where fast and slow feedbacks become deeply entangled? When the collapse of an ice sheet or the slowdown of the Atlantic meridional overturning circulation fundamentally rewires the atmospheric circulation patterns, will there come a temperature threshold where our historical training data is no longer just incomplete but fundamentally obsolete?
Will the patient's anatomy change so much that our historical X-ray machine simply can't read the bones anymore? That is, wow, it is something we are all going to have to grapple with as we push these emulators further into the 21st century. Thank you for joining us on this deep dive into the bleeding edge of climate machine learning. Keep pushing the boundaries, and we'll see you next time.